In this lesson, we introduce the mathematics of apportionment. We're going to start by exploring Hamilton's method. So here's an example of what's known as an apportionment problem. Mom has 50 pieces of candy. She wants to divide them among her 5 children. But she wants to use this as an opportunity to teach her children about the relationship between work and reward. So she announces to the kids that the candy is going to be divided among them at the end of the week in proportion to the amount of time each of them has spent on chores that week. So if you work twice as long as your brother, you're going to get twice as much candy. So here are the numbers at the end of the week. Kids kept track of all the chores they did. Alan spent 150 minutes on chores, Betty 78 minutes, Connie 173, etc. Okay. So there were 900 total minutes of work done by the 5 children combined, and there are 50 pieces of candy to give out. So we want to figure out how many minutes of work correspond to 1 piece of candy. Okay, so I'm going to take 900 minutes divided by 50 pieces of candy and figure out how many minutes corresponds to 1 piece of candy. How many minutes did you have to work to earn a piece of candy? 900 divided by 50 is 18 minutes per piece, for 1 piece of candy. All right, how many pieces of candy did each child earn? Well, we have to figure out how many sets of 18 minutes did they work. So Alan worked 150 minutes, so I'm going to take 150 and divide by 18, which gives me 8.3 repeating. Okay. So I did that. I did 150 divided by 18 to get the 8.3. Said he worked 150 minutes. Every 18 minutes that you work earns you a piece of candy, so he earned 8.3 pieces of candy. All right, 78 divided by 18 is 4.3. And I'm rounding these. It's actually 4.3 repeating. 173 divided by 18 minutes is 9.6. And then Doug, 204 divided by 18 is 11.3. 295 divided by 18 is 16.4, if you round it. And total, 900 divided by 18 should give me all 50 pieces of candy. And when I add up the pieces of candy that I gave to the kids, 8.3 plus 4.3 plus 9.6 plus 11.3 plus 16.4, you get 49.9. Doesn't quite come out to 50 because I rounded a little bit as I was writing those numbers down. So the real problem occurs. What makes this a difficult problem to solve is that if your individual pieces of candy can't be divided into pieces, and you have to give out all 50 pieces, Mom has some decisions to make. Like, these are pieces of hard candy. She can't give a third of a piece. Okay, so she has to decide how many she's going to give based on the fact that Alan earned 8.3. Does she give him only 8? Does she give him 9? Does she give everybody the lower number and then she eats the leftovers? Maybe. So let's see. Our country has to solve this problem every 4 years, right? Apportioning the electoral votes seated and seats in the House of Representatives is a slightly higher stakes problem, apportionment problem, than giving out candy. How to do it has been a recurring debate in U.S. history. So we're going to study several historical ways that the United States has solved this apportionment problem, as well as our current method of apportionment. So some vocabulary that we're going to refer to as we do apportionment problems, because this is so often a political problem, and we're going to think about it in terms of our country's electoral college and House of Representatives, we're going to use the term the states to name the parties that have a stake in the apportionment. In the candy problem, the children are the states. They're the people, they're getting stuff. That's who we're giving things out to. And then the seats, that describes the set of identical indivisible objects being given out. So in the candy problem, the candy is the states. Candy are the states. An apportionment method is a systematic method that divides the seats among the states. The standard divisor, the ratio of the total population to the number of seats. So it measures how many people per seat. How many people get a representative in Congress? How many people do you need to get a representative? In the candy problem, our standard divisor was 18. You had to do 18 minutes of work to earn one piece of candy. Standard quotas, these are the exact number of seats each state should get if fractional seats were allowed. One way to calculate this is to take each state's population and divide by the standard divisor. In the candy problem, Ellie's standard quota, the exact number of pieces of candy that Ellie earned, is 16.4, right? We did 295. We divided that by the standard divisor of 18, and we got 16.4 as her standard quota, the exact number of pieces of candy she earned. Upper and lower quotas. So the lower quota is the standard quota rounded down, and the upper quota is the standard quota rounded up. In the candy problem, Ellie's lower quota is 16, right? You round 16.4 down and you get 16. And then her upper quota, round 16.4 up. This is a little weird because I know the 0.4 typically tells you to round down. But if you take 16.4 and go up to the next whole number, you get 17. So Ellie's lower quota is 16 and upper quota is 17. All right, so our first historical solution was proposed by Alexander Hamilton. This method is comprised of 3 steps. You calculate each state's standard quota. That's the exact number of seats each state should get. Then you give each state its lower quota. Everybody gets at least their rounded down number. Then there's going to be some extra seats, and you give those surplus seats one at a time to the states with the largest residues. Residue is just a fractional part until there are no more surplus seats. So we're going to use Hamilton's method to finish the apportionment for the candy problem. So Alan, his standard quota was 8.3. We did 150 divided by 18, and we got 8.33333. His lower quota is 8. He gets at least 8 pieces of candy. Betty gets 4, Connie gets 9, Doug gets 11, and Ellie gets 16. Everybody gets their lower quota. Then let's add those up. 8 plus 4 is 12, plus 9 is 21, plus 11 is 32, plus 16 is 48. So I have 2 pieces of candy left. I only gave out 48 pieces of candy by giving out the lower quotas. So 2 pieces of candy remain. Mom could just eat them herself, right? But we're assuming the rules are you have to give out all 50 pieces of candy. So who gets the extras? We're going to look at the residues, look at the fractional part. Who was closest to getting another 18 minutes of work done, right? So Alan has 0.3, Betty 0.3, Connie 0.6. She's closer to getting a 10th piece of candy than Betty or Alan are to getting an extra piece. Doug 0.3 and Ellie 0.388. Okay, so I have 2 pieces to give out. I'm definitely going to give one to Connie. That 0.6 is higher than all the 0.3s. And then I'm going to give another one to Ellie because 0.38 is bigger than 0.33. So Connie and Ellie were closest to getting to another 18 minutes of work done. So they each get an extra piece of candy. Then we add the lower quota plus the surplus together. Alan just gets the 8. Betty gets 4. Connie gets her 9, her lower quota, plus one of the extra pieces, so she gets 10 pieces of candy. Doug gets 11, and Ellie gets her lower quota of 16, plus one of the surpluses, she gets 17, And when you add them up, you should have given out all 50 pieces of candy. All right, so I'm going to have you, at this point, turn to your activities, work through them. Remember to check your answers. They appear directly after the activities. And let me know if you have any questions.